All right, hi everyone. So I'm presenting joint work with Warren Powell, and the title of our talk is Optimal Policies for Risk-Averse EV Charging, and this is when we're interacting with the spot market. So we got this problem from industry, and in fact, Google recently filed this patent called a Mediator Device for Smart EV Charging, where they basically developed this apparatus that allows an optimization service up here to control charging an electric vehicle, to control the charging rate. So they're able to communicate with electric vehicles to control the charging rate, but then they say that in many cases, it's not really necessary to charge the EV battery at the full rate. And the reason for this is, for example, EV drivers may drive their cars to work, plug it in all day, and then come back later to pick it up. But the charging only takes a few hours to actually finish. So the question that we want to ask is, how do we optimally operate this charging station when the customer is away for some uncertain amount of time that we may not know, so a random amount of time? And this picture kind of illustrates the type of policy that we might want to use. So there's going to be opportunities when the prices are high that you want to delay your charging to stay idle, and when the prices are low, you want to continue charging. So the problem here is that every time you delay charging, you incur some additional risk of the customer coming back to an undercharged EV, and in that case, you will have dissatisfied or upset customers. So that's the main problem that we're going to look at. And we have a model here. The main parts of our model is that there's a spot price process, there's an amount of energy in your battery, and then there's a charging decision XT. So these things are the three state variables of our model. And in addition, we have this indicator process that tells us if the customer is away, back, or has left with the vehicle. And we also model this charging fee and then the cost of a dissatisfied customer, but I won't get too much into that. And the cost function that we want to optimize is the cost of energy minus this charging fee per time period, and then add whatever cost your dissatisfied customer is going to incur you over, into the future. And it looks something like this. And the framework that we're going to use, since risk is very important in this topic, we decided to go with this risk-averse MDP type of formulation. And this is something that's been popular in the OR literature, popularized by Andrei Rudzinski in 2010 in his paper. So the basic framework here is that if we look at the risk-neutral objective function, which is typically just to maximize or minimize this expectation of the sum of costs, you can write it out like this if you just split up the expectations. So the expectations over time. So any time you just minimize the expected cost into the future. The risk-averse analog is just to replace these conditional expectations with these so-called one-step conditional risk measures. And we're going to parameterize these risk measures with a lambda and an alpha. And what that means is lambda is going to be a weight that you put on to the tail of the distribution, so the upper tail, so the high costs. And C-var is a risk measure that measures the average cost above some quantile level alpha. So as lambda increases and as alpha increases, we're more risk averse. So this is the risk measure that we're using in our problem, in our sequential problem. And what we're able to show is that the optimal policy under all of these conditions takes a form like this. And this is called an order up to policy. So basically, when you're below a threshold that depends on the price and depends on the risk parameters beta, you charge up to as close as possible as you can get to this threshold. So X max is how much you can charge at any particular time interval. And then if you're above this threshold, you simply don't do anything. So this is a common inventory type policy. And it's actually not that surprising because the risk measures that we're using are convex. And that's the main reason we can get this. But what would be more interesting for us to look at is how do these policies change if we were to vary the risk parameters beta? And that's something that's not really been studied. So something that we want to look at is this, what we call the spectrum of risk-averse policies over some set B. And what this means is if we can know what this looks like, then we have a way of tuning our risk measure, which is something that people don't really know how to do right now because it's hard to say what alpha and lambda mean in a practical situation. So this is a way a manager of the charging station can tune the parameters beta, and also while tuning, they have the assurance that the policy is going to be optimal under some instance of the risk-averse MDP specified by beta. And this picture here just shows that not all threshold type policies are going to be optimal under some risk parameter. So this is not too simple. So we want to understand what this set here looks like. Okay, so the main question here is, how does this threshold behave as a function of beta and p? And the second question is, if we want to understand this whole set of policies, we have to solve like hundreds or maybe thousands of MDPs to get a good handle on what it looks like. So the second question we want to ask is, how do we approximate this set of policies in a way that's computationally feasible? And our research goal in this paper was to analyze question 1 theoretically, and then use this result to develop an approximation technique for question 2. Okay, so this is the main result that we were able to show, which is that as you increase beta, your threshold policy stays the same, but it's going to relax a little bit. And that kind of makes sense, because beta is the risk aversion that you're doing. And then the opposite kind of holds for p. As the p spot price increases, you're going to charge less. Okay, so this is what it might look like here. We have lambda and alpha, so it's increasing in both directions. And then if we plot different values of p, it's going to be decreasing. But in order to generate these figures, each of these points is a full MDP. And it takes us approximately 20 minutes of CPU time to solve for one of these MDPs. And to generate this entire figure, we need to solve, I think, like 400 of these MDPs. So it took like 5 days of computing time to solve this. So what we propose is that we use the structural result that we got from the theorem that we had, and do a statistical fit by enforcing this monotonicity. And we use polynomial regression. And we were able to do this, get these fairly nice fits. So we only sampled like 10% of the points here, and get these pretty good policies from 93% up to 99% optimal. And this approximation only took 10% of the CPU time to do. And the idea is that if we are able to have an easy approximation of the whole space of risk-averse policies, then we can simulate any of these policies and then perform all sorts of analyses of what these policies look like in terms of other metrics of risk and reward. And I have some of that in the poster. And in general, we can study EV charging policies without having to do much computation. And any questions? Thank you. Yeah.
Charging stations have another factor, which is that being occupied means that there's a risk that someone needs to charge their car, they show up and they can't do it. How do you take into account the cost of that?
So we didn't take into account directly, but we did implement the method of charging where every 15 minutes that the car is there, they have to pay a fee. So that I mean, the thought is that if you implement this kind of charging at this rate, then people will be less likely to do something like that. Yeah. And there's also the other method where they just, you can leave the car as long as you want, but you pay by the amount of energy you use. And in that method, people tend to leave their cars for longer.
How is the expected time of return of the driver established?
That we actually don't have any data for. If anybody knows of any data source for that, I would actually.
I'm assuming it would be car specific and event specific.
That's true. Yeah. So I know in parking garages, the people that we talk to, people tend to leave it, up to lunch and then maybe come back later. But
okay.
Yeah. Thank you.
Other questions? Thank you.